Good afternoon, everyone. My name is Aziz Sief, and today I would like you to present my paper called GOHAG, GANs Orchestration for Human Actions Generation. I'm a master student at Inha University, and I'm very excited to be here in this conference and present my work. So let's get started. So the table of contents is the following. So I decided to preserve the same structure as in my paper, and yeah, let's start with introduction. So development of generative adversarial networks, or so-called GANs, made a huge impact on content creation applications. Faces generation, human pose or image generation, and as well as the video generation task plays a very important role right now, since the development, the human-specific, human-centric applications. And however, image generation and video generation tasks, they are similar in some case, but there are some specialties in each of them. So video generation task, we need to consider the scene dynamics, frame dependency, and content consistency, which makes this task pretty much harder and complicated rather than just one simple image generation. So in this work, we will concentrate on this area. So basically, the main purpose of this work is the proposed framework that actually takes the user-defined action class and generates a human action video. So we employed here the work of three separate independent GANs. First generative adversarial network is a post-sequence generator. The second one is the post-sequence optimizer that actually optimizes the result of the previous GAN. And last, we have a frame sequence generator, generative adversarial network, that creates a sequence of frames and combines together, in combination together, we have the video file. So all this creates our one framework, which is called the GANs Orchestration for Human Actions Generation, or how we call it as GOHAG. There are many related works on video generation tasks, however the following ones will be closer to our work. So the first one is the post-guided human video generation. Basically, they are also applying multiple GANs, where the first GAN, which comprises of a set of LSTM layers inside, takes the initial input pose and creates the pose sequences based on initial pose, and then later, using another GAN, they are trying to condition it with the target pose to generate the frame. And the next one is the deep video generation, prediction and completion of human action sequences. Here they use two generators in order to create the sequence of poses. Generator number one tries to create the poses from noise, which is embedded into the class of action, and the second generator tries to reuse the first generator multiple times in order to create the sequence of poses. And next, they apply the similar technique with GANs in order to create the frames. However, we have another method, another approach to take a look to this problem, and we called our method as GOHAG. GOHAG, this is GANs Orchestration for Human Actions Generation. As you may see here in the picture, we have two different stages, and the figure number one, you may see that our first stage takes the action class, which is defined by the user, and employs here two GANs. This is PGAN, which is poses generator GAN, and the POGAN, or poses optimizer GAN. And in the stage number one, we are generating sequence of poses. In the stage number two, we will take the sequence of poses from the previous GANs, and using our FGAN, or frames generator GAN, we will create the sequence of frames. And now let's talk about the first stage, or pose sequence generation stage. One of the ideas in this work is action representation. So we have sample pose here, sample skeleton pose, which has 14 points in 2D. So it has X and Y coordinates. But if we will transfer it into one-dimensional space, we'll have 28 points. And for each point, we are not trying to learn exact position in the space, but instead we're trying to learn the pattern, how particular point changes for the particular action here. So now let's talk about our GANs, actual networks. So this is the PGAN, or poses generation GAN. This is the architecture of the PGAN. We have generator and discriminator here. So the main purpose of the generator is to take the action class label from the user and generate the poses a sequence, or basically the action representation that later will be converted into sequence of poses. However, the discriminator will take the generated action representation and as well as initial given class label and tries to identify whether the given image or action representation is real or fake. So by doing so, it generates the sequence of poses, and POGAN, or poses optimization GAN, will work later. So if you will take a look to the figure number 4, this is comparison of POGAN optimized pose sequence and generated by PGAN. So this is real points, and this is PGAN generated. As you may see, it has different noises here and instabilities. What POGAN does is it optimizes the pose sequence and removes noise and smooths a movement. As you may see here, this particular noise in the PGAN is removed after the POGAN. So basically we employed here image-to-image translation using cycle consistency adversarial networks, or simply saying cycle GANs, in order to perform this task. We have real image domain and we have fake image domain. So basically we are trying to reconstruct this image. So our main idea is to look at the noise removal as a style transfer. So next, this is the second stage, or the stage where we will take the generated pose sequences in order to convert them to the real frames. So using our frames generation GAN, based on the high resolution images synthesis and semantic manipulation with conditional GAN, or simply saying the peaks-to-peaks AGD network, we will create the generated frames. So basically for training, we will use the poses and as well as the frames. So basically we will condition our GAN, conditional GAN, with the target pose and as well as the frame. So basically speaking, once the stage number 1 will produce the sequence of poses, our FGAN will create a generated sequence of frames. And this is the results of GOHAG. Here you may see the generated poses sequences and the textured frames here. And these are the sample generated results. Now let's talk about the experiments we've done. So we used public dataset called a dataset of 101 human actions classes from video in the wild. Basically there are many action classes there, but we only took jumping jack, jumping rope, and tai chi classes. So we took all videos of the following classes and estimated the poses using the OpenPose library. So we took 14 points for each frame, and we created a dataset that has the pose to frame matching. So we started our evaluation with the poses generation stage, and in this experiment basically we want to identify the pace of real movement, GOHAGs, and deep, which is the one of the related works. So we use Euclidean distance, or L2 distance, to measure the distance between the each consecutive poses, and by doing so to identify pace of movement. And following the results, as you may see, GOHAG has the better and closer results to the real pace of action rather than the deep generated one. For the frames generation stage, we apply the video quality evaluation, where we use the PSNR, or peak signal to noise ratio, and SSIM, or structural similarity index metrics. So in both metrics, the higher the better. So in PSNR, basically we're trying to find out the ratio of the real signal with the noise. So here the deep a bit better than the GOHAG. However, in SSIM, which actually measures the similarity between two images, we can see that the GOHAG outperforms the deep. In the next experiment, we have modern techniques called inception score and fractured inception distance. Both metrics, they use inception classifier to make the measurements, where the inception score measures how real generated data is, and it concentrates to the meaningful and the diverse results. So we want clear and not blurry images, and as well as the images to represent different class labels. Here, inception score, the higher the better, whereas the fractured inception distance compares mean and covariance of real and generated images. So basically, we have distribution of real images and distribution of generated images, and we want the distance between the distributions to be smaller. So the smaller the better here. And following comparison table, you may see that GOHAG outperforms deep in both metrics. And our last evaluation was based on the user evaluation. So we created a survey that consists of different sizes of images of GOHAG and Jeep and real images. So participants had to distinguish the real set of images from GOHAG or Jeep generated, and we provided different size of images. So basically speaking, the 31 participant in the volunteers in social media had to answer the question to find the set of real images. And as you may see here, we provided the different size of images, and here is the resulting figure. So this is the percentage of correct answers and the picture size, and the lower graph considered to be the better graph. Even though deep generated images shows better result in the small size images, the GOHAG starting from 100 by 100 shows the same or even a better result than the deep generated ones. And to make a conclusion, we proposed another method based on generative adversarial networks and their orchestration for human action video generation, or GOHAG. We proposed a special way of representing human actions, and we evaluated our results quantitatively and qualitatively and showed better results over existing method. And we've achieved a production of plausible and high quality and realistic human actions. So thank you very much for your attention, and if you have any question, feel free to contact me. Thank you.